Hello there and welcome back again. This is Mr. Spinks and we are on section 2.2 in NAM's class producing the last video from section 2.2. Now this isn't a tough concept, guys, but I need you to really focus this time because people have trouble with this one. This is one that's been missed in previous years. Look, we're talking about distinct subsets today. Now the question here says, what is a distinct subset? How is it different from a subset? So our definition here says distinct subsets are all of the subsets that can be produced from original set. So they are subsets, but it's all of them that you can possibly produce from an original set. Now there's a formula that helps you to determine the number of distinct subsets that can be produced from a set. If we make n equal to the actual number of elements within the set, then the formula 2 to the nth power will tell you how many distinct subsets are produced. Easy stuff. Simple formula. Please remember it as we go through because people do forget it each time. Now the first question that's being asked for me from this first example is the number of distinct subsets that are possible from this set. Well, as I look, there are a total of 3 elements here. So n is 3 in this case. And our formula was 2 to the nth power. Well, if in this case, if n is 3, there will be 2 to the third power distinct subsets that can be produced. Now don't call it 6, because 2 to the third power is 2 times 2, oop, there's a times there, times 2. And since 2 times 2 is 4, and 4 times 2 is 8, there are a total of 8 distinct subsets of this set. The second question asks me to actually list the number, or list what they are. Not how many of them are there, but what are the actual distinct subsets. A couple of ways of going about this. Some people start with the original set. Obviously, the original set, which has M, R, and H, is a subset. Next up, they go from 3 down to 2. So with 2 elements, I could do M and R. I could do M and H. And I could do R and H. Easy stuff. That's 2. Down to 1, a subset that has 1 element. Well, it could be M, R, or H. And it's nice to know how many subsets there are before you actually write them out, because you're going to end right there and think, I'm done. I've got all of them. I listed them out. Well, if we count here, I count 1, 2, 3, 4, 5, 6, 7. And we're supposed to have 8 of them. So we're missing 1. And the one we're missing is one that will be there every single time. We talked last video about the fact that the null set is a subset of every set, and that one will be there every time. Therefore, you see a total of 8 of them. There are all the distinct subsets of our original set. Final question, how many of these distinct subsets are also proper subsets? Well, if you remember proper subsets meant that they were subsets but they weren't equal. So I'm going to look here and say how many of these are actually equal to my original set. Well, as I look at my original set, I only see one of them, this one located right here, that is actually equal to it. Therefore, it can't be a proper subset. All the rest of them can. Well, as I count, there are a total of 7 other subsets here. Therefore, there are 7 distinct subsets that can also be proper subsets. Moving on, last question we've got right here is the same idea, just helping you to understand it. We're now using a set that has 4 different elements. Therefore, the number of distinct subsets, which is 2 to the nth power, is going to be 2 to the 4th power. 2 to the 4th power is 2 times 2 times 2 times 2, which is 16. Total of 16 possibles. It's nice to know, it's kind of a pain that we're going to have to list out what all of them are, but it is nice to know how many of them there are going to be before we start. Now, let's talk about what they are. And I'll set you up with the way that I normally do this. The way that I normally do this, I always start with the null set, because I know it's going to be an actual set, and then I start from low to high. I'm going to start with the ones that have 1 element in them. So I'm going to start with B, L, U, and E. So that's all of the subsets that have one element of them. Then I'm going to move on to 2. Moving on to 2, I can do B and L. I can do B and U. I can do B and E. I can also do L and U. I can also do L and E. And I can also do U and E. So those are listed out, all of those which have 2. Then I'll move on to 3. So I kind of move up. I think this is a little easier. It's your call. You can go high to low or mix it in between. I just need all of them. Just trying to help out. So I've taken care of those, the null set, those that have 1 in them, those that have 2 in them. Now I'm going to go to 3. We can go B, L, and U. We can go B, L, and E. We can go L, U, and E. We can go, so looking there, I think those are all of them that have 3 of them, and I'm going to count here now. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Total of 14 that we've got here. So we're looking for what we missed. Well, I missed one of the ones that had 3 of them in there. I missed the B, U, and the E. My mistake. Got that one now. And the last one, of course, is the full set that has all the elements, the one that's equal. There they are. There's all 16 of them listed out. And on the last question, how many of these are also proper subsets? It's all of them that aren't equal. And this one down here, the last one, is the only one that is equal. Therefore, there will be 16 minus this one, or a total of 15 of them that are also proper subsets.